In our last lecture, we learned all about circuits with inductors. We learned all through the circuit analysis, which I will review for you very briefly, because we will be building upon that today. Also, at the very end, we began to consider issues of energy and inductors and learned that the energy stored in an inductor has this interesting quadratic type of a formula, 1/2 Li squared, which we will build upon not in this lecture, but actually in the following lecture. In terms of dealing with circuits that include inductors, the main new thing we learned in terms of the basic fundamental analysis is how to generalize Kirchhoff's second law. That's his voltage loop law. We learned that we can massage things so that we come back to exactly the same form of the law, that the sum of the so-called effective voltages now, that the sum of those voltages around any closed loop must be zero, where we include a new type of effective voltage in our law, which is the voltage contribution from each inductor, which comes in the form of plus or minus L, where L is the inductance, the constant which characterizes the inductor, times then the characteristic formula for the voltage actually involves the rate of change of the current, di dt. Once again, as always in this course, when dealing with circuits, we have to be very careful with our signs. We should always write either plus or minus and then circle the appropriate one which applies to our particular equation. In this case, the mnemonic for remembering the sign works in exactly the same way as that for the resistor. In other words, we take our presumed flow of direction of the current, i.e., that direction of flow which we would consider a positive current going through the inductor, and then the upstream side, in other words, the incoming side, we label plus, and the outgoing or downstream side with respect to that presumed direction of flow, we label minus. Then, as we go around our Kirchhoff loop, if we happen to traverse the inductor from plus towards minus, that would be a downhill type contribution. We would select the minus sign. On the other hand, if we were going in this direction, going from the minus towards the plus, that would be uphill. We would then choose the plus sign and then would generate an appropriate equation to analyze our circuit. We then analyzed one of the simpler but yet classic circuits involving an inductor, the so-called LR circuit, because it involves an inductor as well as a resistor. In this case, we have an EMF curly E, which is driving our circuit, and a switch that we close at time t equals 0 to complete the circuit. When going through this analysis, we learned not only the details of carrying through the analysis and derived an explicit form for the current as a function of time, which we will discuss in a moment, we also learned two very important rules about how an inductor behaves as we go towards either short times or long times. And these are always very important levels of understanding to have of these two particular behaviors if we want to understand at least qualitatively how any particular circuit will behave. In this case, what we learned is that as we go to short times, the current must be a continuous function. That is because the differential equation involves a time derivative, and if there were any discontinuities in I, that would correspond to an infinite voltage, and since we do not have infinite voltages available to us, the derivative of the current must always be finite and defined, which implies then the current must be continuous. That means that after we throw this switch, the current through the inductor will always be exactly what it was before we threw the switch. In other words, the inductor acts like an ideal current source, either with a zero current that it maintains, at least for a short period of time, as it would in this case, because the initial current was zero, or if we were in a different situation where we were, say, opening the switch, in that case, then the inductor for a short period of time would actually maintain the current through it. There's then the opposite limit as time goes towards infinity. In this case, just like with the capacitor, the circuit element behaves much like it appears in the diagram. In the diagram, the inductor appears just as a curly connected wire, and indeed, as time goes to infinity, the inductor actually acts like an ideal wire. In other words, there is no voltage across it. You can simply replace it with a wire and analyze your circuit to determine the appropriate behavior. We then went through and wrote down the actual differential equation and solved it. Here is the solution we came to via our favorite method of separation of variables. You will notice it has all of the features I just described. As time t here along this axis goes to 0, the current actually goes to 0 to be continuous with the fact that the current must have been 0 when the switch was open. As time then goes off towards infinity, we see that the current is the EMF divided by the resistance, which of course, once we connect this switch, if we just had a battery, a switch, and some wires connecting through a resistor, that is our classic result then for the current. So it approaches that then exponentially with an exponent that's characterized by a certain time scale. Here I've rearranged the equation a little bit to write it in the classic form t over tau, where tau then is the exponential decay time. And if you do a little bit of the algebra here, you can see that the time constant tau for this LR circuit would indeed be L over R, because tau has to appear on the bottom in that exponential. Graphically, there's a quick graphical construction we can use actually to extract tau. As you remember, when we have exponential behavior, if you take a linear extrapolation of the initial behavior and ask where that linear extrapolation actually crosses the final asymptotic value, the time at which that occurs actually corresponds precisely to that decay time. So that was our analysis of the LR circuit.